In this video, I'm going to talk about the forces in 2 dimensions, where a force is no longer acting parallel to the surface that the object touches. So we're going to put a force that's pulling up at an angle, and we're going to do a force that's pushing down at an angle. But before I do that, I'm just going to talk a little bit about the theory with no numbers. And let's see if we can do a free body diagram, if we can write our equilibrium statements. In other words, if we can write our F net equals ma, or the sum of the forces equals ma. So I have an object here, a block on a flat surface. And I'm going to pull with a certain force. Let's just say I call it Fa, applied force. And that force makes an angle theta with the horizontal. And then my forces are mg, pull of gravity on the object, and let's just say that there is some friction. Okay, and there is a normal force. Now, if I'm pulling up, the normal force should be less than the weight, and the reason for that, because as you're pulling up and to the right, as you're pulling actually to the right, you're also pulling up. So you kind of like the contact between the block and the surface is weaker. In other words, the block is not pushing as hard on the surface as if this force was parallel. So my normal force should be less than the mg. And again, the reason for that is because the Fa, or the vertical component of Fa, will help support the block. It will not just be the surface or the table that's supporting the block. You're also providing some of the support by pulling out, but you're also pulling up, even though the object never leaves the surface. And we're going to say that this object has a mass m. Now we're going to write the sum of the forces in the x direction equals ma in the x direction. And I'm going to write the sum of the forces in the y direction equals m times the acceleration in the y direction. Now these are all vectors, of course. Okay, these are not scalars. Now in the x direction, this Fa, which I'm going to draw here and erase because you're not supposed to have the components on the diagram, it's got a component pulling it to the right. So when you pull in an angle like that, you're pulling right and you're also pulling up. So this is the x component of Fa, and this is the y component of Fa. And we're going to erase those later. They cannot stay there. So what I'm looking at is like, just we're going to the right here, right? Or we could be moving to the right, we could be not moving to the right. Could be just pulling, but no action, nothing is happening. So I see that the Fax, and don't memorize this stuff, you have to do it, minus the force of friction equals. Now you can have 3 cases here. You can be pulling with that force, but it's not enough to move the object. So which means your acceleration is 0. It's still at rest. You could be pulling with a force and going at a constant velocity, which means there is no acceleration again, which means this Fax is exactly the same size as the friction. Or you could be accelerating to the right if this Fax is greater than Ff. Right? Now you're going to see why I removed the subscript from the x side once I do the y direction. In the y direction, as far as we're concerned, we don't care what's happening to this object right and left. We're looking at it, what's happening to it up and down. So the acceleration is 0, which means the up forces must equal the down forces. Now here is my up forces. It's Fn plus Fay, because that's pointing up, equals forces acting down, because there is no acceleration. The object is at rest vertically, not horizontally, not necessarily horizontally. That's why I didn't put a subscript here. Now, the Fax is just going to be the Fa cosine of that angle, theta, minus the force of friction. Now, the force of friction is mu times Fn, if you need it, equals, and then you look at your three cases. The Fn here plus Fa sine of the angle is mg. Now you pretty much have these equations, and depending on what you're looking for, you have to rearrange them and figure out what you're looking for. So if you want to get Fn, you can get it from here by isolating it here and plug it in here and find whatever you're looking for. Now I'm going to do an example where I'm pushing down on the object. Now I told you in the past that we don't want arrows going into the object. The arrows have to be going away from the object. So instead of pushing down this way into it, I'm just going to say, you know what? It's like pulling down this way. Same thing. And this angle here that this force makes with the horizontal is theta. And this is still my applied force. Okay? Now my statement in the y direction would be different. So let's look at it in the x direction. So here is my x component of Fa, which is also a vector, and here is my y component, which is pointing down this time. Okay? Because if you're pushing down, it means you pushing to the right, and you're also pushing down. If you're pushing down at an angle like that. All right, so it's going to be Fax minus the force of friction, and then you do your three cases. You might be pushing down, the object doesn't move. You might be pushing down and the object moves at a constant velocity. In both cases, you get a 0. One 0 is for static equilibrium, and the other 0 for a different reason, for dynamic equilibrium. Or you can get the mass times the acceleration. On the other side, the Fn should be bigger, because conceptually the desk or the surface has to provide more support, because now you're pushing harder on it. There is more push on it. It's not just the mg that's pushing down on it. It's not just the push of this block, but it's also the push of Fa that's pushing down. So that component is pushing down. So that should be, this Fn should be bigger in size than mg. In other words, the mg and the Fay should add up to equal Fa. So the force up is just that Fn by itself. That should equal to mg plus the y component of the applied force. And you can do whatever you have to do with this. So I'm going to throw in some numbers here, actually. So I'm going to say this angle here is, I don't know, 60 degrees. This applied force is 100 newtons, and I'm going to make this mass 20 kilograms. So let's hope the numbers work. So I'm going to go ahead and find out what Fax is first and Fay. So Fax is Fa cosine of 60. Fay is Fa sine of 60. Now we know cosine of 60 is half, so this should be just 15 newtons. And the other one is 86.60 newtons. And I'm going to say that there is a coefficient of friction of 0.1 between the block and the surface. And here is my statement in the x direction. Now I don't know if it's going to accelerate or not, so maybe I should figure out what Fn is first, right? Yeah. And then find out what the friction is, and based on that I can decide. Because if the friction turns out to be exactly as Fax, then there will be no acceleration, which means like we're probably just going at a constant velocity. And I'm saying that this is kinetic, so I'm going to set this up so hopefully that it's moving. So Fn equals mg, which is 200, plus Fay, which is 86.60. Right, so that's 286.60 newtons for Fn, which means the force of friction is mu times Fn, which is 0.1 times 286.60. So that's 28.66 newtons. So Fax is bigger than Ff, so we're going to have to accelerate to the right. And I'm going to try to find the acceleration here. And sometimes you might be given the acceleration, you have to find force of friction, coefficient of friction. You can pretty much manipulate these equations any way you want, so you can find what's missing. So Fax is 15 newtons minus a friction of 28.66, a mass of 20, acceleration. So I take out my calculator here. I get 50 minus 28.66. I divide that by 20, and we get an acceleration of about 1.07, I guess, meters per second squared. Now I'm going to redo the same exact problem, except this time I'm going to pull up on the object and see how that's going to change. So Fa is 100 newtons, and here are your components, which we'll erase later. So this one is 86.60, and this one is 50 newtons. So Fax is not going to change because I'm keeping the same angle here. I think I did 60 degrees, yeah. The Fn will change. This statement will be different now. So that should be Fn. So this is going to be shorter, basically. Okay? So it's going to be Fn plus the y component of Fa equals the mg. So which means Fn is going to be mg minus, and we expected it to be the contact between the surface and the block to be weaker. So if we do the math there, minus 86.60, oops, 200 minus 86.6, so we should get 113.4 newtons. So we'll replace this here. You got the idea, right? So my friction should be 11.34 newtons after I put in 113.4 here. So that should be, and that should have been expected now, because you're going to have less friction because the normal force went down, which means the block is not pressing as hard on the surface, which means the surface does not have to support it as much. So 11.34. So if we do the math here, divide that by 20, I should get 1.93 meters per second squared, and should have been expected to be greater than before, because now you're not pushing down on the block, so it's going to accelerate at a higher rate, or it's going to speed up at a higher rate. And that's pretty much it for the forces at an angle. So in the next video, I'll do some examples. See you later.